Welcome back. And this afternoon, we will have 5 speeches in this room, plus 1 keynote speech. Our next speaker is an expert, over 25 years experience in computer vision and deep learning. He will show how AI and cameras can automatically detect waste. Please give a big welcome to Tom.
Thank you. Well, I'm honored to be in this venue on the main stage, so I will... Oh, next one, yeah. So today I will talk something about using computer vision in the context of waste and checking how we can find stuff in waste that shouldn't be in there. So it's really about cameras and models and world models that are used nowadays. So I'll first talk a bit about what PMD is, how the waste is collected. Then we should have a look on how do you collect good data, because data collection is not really a very simple thing. Most people think, okay, you have data, but in the end, data collection always takes a lot of time and effort and safety issues and all those kind of things. Then we look through the pipeline that I developed. So in the pipeline, there is object detection, object segmentation. We have anomaly detection, and then we have some final results I want to show. So a little introduction on myself. I'm a computer vision engineer for about 25 years, so I was already around before all the AI came up. But AI has made our life much easier. So I studied optics in Enschede, and since 2013 I work as a self-employed engineer. And I designed a lot of things. So first you see a roof tile recognition system. I automated Henk, and Henk knew everything about roof tiles, but he went into retirement, so he had to be automated. The next is a project on plastics, where we had to detect the kit tubes. So this was really a game changer for people in the plastics, that you could do with like 100 images. You could easily detect kit tubes with a computer, because people were still picking these things out. The middle one is I worked a lot on the printing press to measure colors in the papers. I have a Grolsch beer bottle because I'm still proud of it. Like 25 years ago, we developed a system that did 10 bottles a second. So that was before all the big computers. And the last thing is a project I did to measure how dirty crates are. These are washed. And then we had a system to look on all sides of the crates if they're clean. So this is typical projects I do for customers. The project I'm talking about today is done for the National Test Center on Circular Plastics. It was founded 5 years ago, and they're really doing industrial scale research on plastic sorting and recycling, and it's really successful. You see here the building, it's colorful. If you go there nowadays, it's 4 times as big, because they just built new halls and got all kinds of nice new equipments. And I should mention that it's sponsored by TKI Energy Industry. It was very important that I should say that. So that is something I managed now. Okay, let's go into PMD. PMD is plastic, metals, and drankkartons. I don't know what the English word, yeah, probably drinking cartons. So a lot of people have these separate containers to collect these at home. And some people have special bags, but basically they're collected separately from the other waste. And when it's waste, it goes into the truck. The truck goes to the transfer station. You see it here on the left. You see a typical transfer station. So the truck comes, the whole truckload is dumped on the floor. And at that moment, there comes an operator, and he's looking into this pile, most times with a crane. He just shovels around a bit. And he's looking really for things that shouldn't be in that container. There are always things in those containers because, no, not because people just throw things in, but sometimes you just don't know that it shouldn't be in there. So it's a manual inspection, and yeah, it takes time, and it's not, yeah, it's very subjective to do this like manually because, you know, if it's Monday morning and you had a hard weekend and you have another idea on what's good or bad. So they asked us, like, could you develop a computer vision system that at least recognizes things that shouldn't be in there? Well, we looked a bit at it at the transfer station over there, and we thought, this is going to be a hard task. So, because yeah, it's a big pile, you know, there are all kinds of objects in there, and when we were looking there, it was also immediately clear that, yeah, you just couldn't have like categorize what shouldn't be in there. They had a list, but the list is not really like how it is in practice. So we decided, yeah, we have to take first some images and gather the data, and well, and the most important, we should do something with what's normal and what's not normal. I always call this like, you have like apples and non-apples instead of apples and pears. So that's, for me, really anomaly detection is. So what we did is we built a very simple setup. You see to the left, we just have, well, it's something this height. We just look down to 1 by 1 meter and a resolution about 1 pixel for 1 millimeter. I think something even better. And to the right, you see, yeah, really the piles where we should detect things in. So it's really like a thick layer of objects that, that are concatenated. So, the data pipeline that we have or designed in the end, this is the success story. So I should talk about all the failures I understood this morning, but the success story is this pipeline. So we have a camera. We get images, of course, from the camera. So the first step we do is we want to detect every object that's there because, well, we want to say something about object level because there are objects that shouldn't be in there. So first we do an object detection. So then we get a lot of object detections in the image. From every detection we want, detection is really like a bounding box. We want to get like really the pixels that are the part of the object. Once we have those, we do a kind of anomaly detection, and then we can decide it's a valid object or not valid object, and we can give back this information to the customers. So the first thing, object detection. Object detection is really, like I said, you want to have like a bounding box around every object that is in the image. So we started out with like the upper images where we have really separate objects just to find, okay, does it work and can we develop? So this is what we did at NCP. We just gathered a lot of objects, put them under the camera, and this is really the data collection that takes so much time and effort because you have to put the objects over there, you have to take a photo, get it back again. So really getting data, getting good data in computer vision is really expensive, exactly for this reason, because you have to do it clearly and good in a good structured way to get your data. So people like me need to be there because otherwise if you just ask somebody, just take some pictures, you end up with something you can't use. So what we did is we made it ever more dense until we got to the last piles, the image on the bottom. These are taken at the actual transfer station. So we took up the setup and we go to the transfer station and we had a crane really putting stuff in there, and then we also took pictures. So we took all the pictures, we labeled 174 images by hand, and then we trained actually we fine-tuned a YOLO model. And well, we got a reasonable precision and recall. So the precision is how accurate you can actually find the objects, and the recall is how many you get. So you can imagine that you have a very precise system that really finds this one single object but misses all the others, then you have a bad recall. So it's always like a mix in computer vision between precision and recall, and you want them both as high as possible. But given the amount of images we had, this is like a reasonable working process. So once we have all the bounding boxes, we can go to the object segmentation. So I did, like I said before, I used the standard YOLO algorithm. So this is one of the big, what we call vision foundation models. So there's a lot of things in vision where you have just models out of the box, and you can just use them, fine-tune them, and you have something working without relying on massive amounts of data. So the other thing for segmentation, we use the segment anything from, I think it's Meta. And that's something that works, well, yeah, it works amazingly out of the box. So you need to prompt. So you need to prompt either a bounding box or some points in the object, and it segments out the complete boundary of the object itself. And once you have the boundary, of course, you can grab out the pixels you need. Well, if you have one thing about failures, maybe I can talk a bit about it. I was first working on this, and yeah, I just trained very quickly a YOLO, and it was not too precise. So I ended up with not so good bounding boxes. And then I did SAM, and well, it kind of worked, but not really good. And then I tried to use some classical computer vision algorithms to find better points to prompt it. And yeah, I got down that line, and yeah, it really didn't work very well. And then I thought, maybe I need better boxes. So I took some time to train a better YOLO, and then it worked like magic. So it really depends on how good your object detection is. So how good can you put the bounding boxes around objects? Then you really get very good results from the segment anything. But the good thing is you just download it. It's 3 lines of Python, and you're up and running. And that's really a thing in at least in vision. You have so much models on Hugging Face, what you could easily use out of the box. You try something, you improve something, and with a few lines of code, you got a part of your pipeline working. So the good thing is now we have objects that you can see from left to right. Left, you have the bounding boxes. Right, you see the contours of the objects. So then we mask out the pixels from the objects, and then we can do something that's called anomaly detection. And anomaly detection is out of distribution detection in feature space. So I assume everybody knows what a feature space is here. One thing on anomaly detection, what you should always have mental note of what's data doing in high-dimensional spaces, because people tend to do is, if you say something about out of distribution, they always draw this nice standard distribution curves, you know, in 1D, and that's really not how it is. In the distribution of data in high-dimensional spaces is always on a ball. So, because you can imagine if you have like 700 features and you have like a random sampling, you will never have a factor of 0, 0, 0, 0, 0. That's very, very uncommon. So the data is really on a ball. And in this case, we didn't have time to really explore all this data and get balls and so on. So we basically did a cosine similarity for cluster membership. And we built up a cluster of the normal distribution to compare to. So to do that, we had carefully selected 1,000 reference objects. We knew, for instance, really this is like something that should be in PMD. And we just gathered the features from this set of common objects to compare the outer distribution to. So the first thing we did was the visual features of the object. So we got this from a standard convex base from Hugging Face. So to the left you see two objects. So one, no, it's kind of clear. It's a blue bag, so that's a typically packaging bag that should be in there. And I got the pixels out and I concatenated or just added it to a big black image that's 1024 by 1024. So this is bit to also capture like the size of the object. And the other one that you see, that's an electric drill, and that's something that shouldn't be in there. So that is really an anomaly. And like I said, once we had this feature extraction part of the pipeline, we just grabbed our 100 objects and we just made a reference. So we had this feature, big feature matrix of 1024 features. That was our reference. And in test time, we had a factor, so a visual factor for each object, and we compared to this 1,000 other objects, and then we did a cosine similarity for the 10 best matches, because we already found that in the reference set there were like different objects, so there were more plastic types or more PMD types or more metal drink packages type. So to capture really like what was normal and compare it to, we took the 10 best matches. And I think a really improvement point is in this kind of things is how good is your reference set. But then we had some results, but still some anomalies were really looking visually comparable to normal objects. So then somebody said to me, why don't you just throw it into ChatGPT? People say those kind of things. I thought, I can try. So what I did is I took an image with the bounding boxes. I sent it up to Gemini in this thing, and I got a really, really nice description of every object. I was really amazed about it, how detailed it was. So I thought, this is nice. How do I do this? I thought, well, I got a text description, but I still need features. So I grabbed some text to features model. It's called All-Mini LM6. I don't know why I selected this, but probably the first I came along. And it puts all my text back into feature space. And from this same set of reference objects, I also send them up to Gemini, ask the questions, and I got back like 1,000 description. So I used that as a reference set. And also did the same trick with the cosine similarity. So then I have like two, what I call anomaly scores per object. Okay, to the left you see what really the answer is from Gemini on this object. So it's nicely made in JSON. And in the end I got two scores. And no, I didn't put in that slide. Okay, I got two scores, and I made a function to combine them to a single score. And what we did then was the big final test. So we made a rack with 4 cameras that really could look at 2 meters by 2 meters. And we put a big pile of good waste underneath the cameras, and we took the images. We ran them through the pipeline, and this was the result. And I was really amazed by the result because this was in a different location. We just set up the cameras and just ran it. And as you can see, yeah, it's a big pile. There are a lot of, yeah, it's maybe not so clear for you, but it's a lot of objects over there. And like, okay, everything is about green, which is good. Eh? And there is only a few things that are not going too well. And then we did to the same pile, we threw in some objects that shouldn't be in there. So it's like the Makita, it's the pet thing. There is a beer thing from Heineken that shouldn't be in there. And everything that shouldn't be in there was pointed out like, okay, this is something that shouldn't be in this pile. So we showed this to the end customer, and they were just as amazed as I was. So when we started out, I didn't believe really that this would be possible. But nowadays, with all the models that are there and what you can try easily, it seems that there is always more possible than you think there is. And I must admit, before we had AI, we wouldn't even think about this. So that's really the great thing. So I would thank everybody for attending this talk. Anybody interested in working at NTCP, it's far from here. It's in Heerenveen in the north. But the team is growing over there, so there are roles. And if you want to do something useful, then you can check out their jobs page. Any questions?
Yeah, I can throw it.
It works.
Sort of. Fuck you. You showed quite a nice presentation with anomaly, but did I understand correctly that you only looked at the visual light as an input, or did you also use different kinds of inputs that maybe are not available to, well, as flashbacks?
What do you mean by other?
From you can go outside the visual range.
No, we did this pure with RGB cameras, so it was pure visual. Normally in plastic sorting, you use a lot of infrared to see what kind of plastic types it is, but this has to be like, this is like an area scan, and it has to be cheap. So we just used kind of off-the-shelf RGB cameras for it.
Thank you.
Yeah, so question for, so as far as I understand, this is kind of still of a research like project.
Yeah.
What's missing to use this in every, basically everywhere? And first question, I have another question. What do you think is the future of using this AI method to improve the recycling?
Yeah, it's a good question. Like you said, well, this was the first research project just to check if this is possible at all, which is quite normal for me to do in this kind of vision project. Just gather some data, try some models, just get a feeling on how hard the problem is, can you solve it? Next stages would be, test it in a real environment. This was really controlled, so then you would hang a camera in such a transfer station, you gather more data, you validate your models, and then you have to think about all the kinds of stuff like how do you keep your cameras clean, when do you take a photograph, how do you couple your output to the truck, to the databases where they want to store all the results. So that is still a lot of, well, I call it always plain old engineering, but it's a lot of work still to do. So the question now is, it's going on over to return on investment, and so those kinds of decisions, which are all, in my eyes, a bit boring, but they're essential to get the money to get the rest of the project going. So, yeah, we're talking about how we could develop a real system now, but yeah, it still needs some more investment. So that will be, yeah, that's a part of the future. We don't know if the end customer who we did this for is still interested to invest more money for this.
Thank you.
Yes, also works. Thank you for the talk. I was wondering if, for now, for instance, it found all the anomalous objects, right, in your test case. What if it doesn't find it? How could you then improve the model? Because you only train on good examples.
Yeah. Yeah, the thing is, that's exactly the reason why we choose an anomaly detection is, and while in more situations, you choose for anomaly detection because it's very easy to gather data of good objects. And if you just go to a transfer station, and I've been there for like 1 day, and I saw to all the objects, and there was like a children car seat in it, a teddy bear, kind of strange objects. So if I would go there, I only see this once a year or something, or only once. So the reason we really choose anomaly detection, like we have no clue what we will find there. So
that I understand.
And if you really want to improve models, then you have to like gather data and data and data from the real situation, check what the model does, get a domain expert with it to check if the output of the models is good.
Yeah, but for instance, if it would not have recognized it would have correctly found incorrectly found your drill as not anomalous.
Yeah.
How would you then improve it?
Yeah, well, the only thing to improve it is you have to go really through the images and check what is going wrong, and then you have to go back to your models and check. Okay, why do I not find visual or textual features, or do I need to add something? There was also in my reference set, I didn't have enough like this dairy cartons that could be in there, so they were not recognized. So they were marked as anomaly because they were not in the reference set. So it's all a matter of how good do you capture really the distribution of normal things. And of course, if it does look really like a normal thing, and the text description is also like a normal thing, yeah, you won't find it. But yeah, in the end, it's how good does it need to be?
Exactly, how good is it now, right?
And I'm pretty sure that the manual, the human operator misses a lot of things and misses more.
Now we have time for the next question.
Thank you for a very nice presentation. Lots of deep work. I'm impressed. Can we scale this up to other solutions that can benefit more people? For instance, in zones where there is waste lying out in the streets, or in other zones that need help cleaning up, and how to detect them, so we can focus our efforts on where it's most needed. Your solution is now focused on waste separation facilities that are tailored for this. But what about communal zones, or even war zones? If we want to help clean them up, would your solution be scalable?
Yeah, well, it really depends on how good data you can get and how good your features you can get. But it's always scalable. I mean, it's computer code, so you can scale it up to everything you want. But I've been thinking before about things. Could you do like landmine detection, which is a big problem? But that's really I read a bit about it, and that's really hard, because to get really detection, or that's really on the detection side, you can't see them because they're a little bit buried under the sand. You really can't find them because the material types is hard. But yeah, everywhere, the thing is, everywhere where you have like a normal situation, you can use anomaly, of course, to detect what's abnormal. So as long as you are able to capture the normal situation, you can use these kind of techniques. But it's always a matter on, like the other gentleman asked, like how much anomalies do you miss, and how much false flags are you willing to accept, and what are the costs of those? So that's but that's the basic, I think, on all what people are doing with data.
Thank you very much.
Okay, you're welcome.
Okay, let's thank Tom for the wonderful speech. Now we will have 5 minutes break, and we will continue at 1:25.